Titan is Saturn's largest moon, a world with rivers, rain, lakes, and weather. On one end, the temperature sits at -179 degrees Celsius, colder than any spot ever recorded on Earth. On the other end, it rains a chemical you'd normally burn in a stove, liquid methane, falling from orange skies onto a surface with more liquid hydrocarbon than every oil and gas reserve on Earth combined. Every other moon and planet we've mapped is either bone dry or locked under ice. Titan is the only other place in the solar system with a working cycle of liquid on its surface. Evaporation, clouds, rainfall, rivers cutting into rock, lakes collecting at the bottom. The mechanics are Earth's. The liquid is not. Water on Titan isn't a liquid. It's the bedrock. At -179 degrees, water freezes harder than granite and behaves like stone. Instead, methane and ethane, simple hydrocarbons, the same family as the gas in a kitchen stove, take over the job water does on Earth. They evaporate from lakes, form clouds, and fall back down as rain. A whole weather system, running on lighter fluid instead of water. One man spent decades trying to convince NASA this place deserved a closer look than a flyby. Ralph Lorenz is a planetary scientist who joined the Cassini-Huygens mission in the early 1990s, years before launch. Most of his colleagues treated Titan as a stop along the way to studying Saturn's rings. Lorenz treated it as the destination. He'd spent his career modeling what a thick, hazy atmosphere over a frozen moon might actually do to a falling object, and he wanted proof, not simulations. Inside the team, the argument got personal.
Why land on a moon we can barely see through that haze? A flyby gets us data with none of the risk.
Because everything interesting about Titan is under that haze. If we don't go down, we're guessing forever.
Lorenz won that argument, eventually. But winning it meant designing for a world nobody had ever touched. Here's the strange part. Titan's atmosphere is about 50% denser than Earth's, pressing down with more mass of gas overhead. Its gravity, meanwhile, is only about 1/7 of ours, close to what you'd feel on our own moon. Thick air, weak gravity. On paper, that's the easiest flying conditions in the solar system. Strap on a pair of homemade wings on Titan, flap your arms, and you could take off. Lorenz calculated it himself. A human being, in the right gear, generating enough lift to fly under muscle power alone, something physically impossible on Earth. But knowing you could fly there and knowing what you'd fly into were two very different problems.
Lorenz and his team had one probe, one descent, and 90 minutes of battery life to figure out exactly what they were falling into.
Here's what most people assume. Titan has liquid on its surface, so NASA and ESA must have picked a landing site the way sailors pick a harbor. A visible sea, a shoreline, coordinates you could circle on a map. That is not what happened. In 2004, when Cassini reached Saturn, no human had ever seen Titan's surface. Not once. A thick orange haze of nitrogen and methane smog wrapped the entire moon, and ordinary cameras simply could not see through it. So Cassini used radar instead, bouncing microwaves off the ground like a bat in the dark. The returns came back as blurry patches of light and dark. Nothing more. Dark could mean a sea of liquid methane, smooth enough to swallow radar waves whole. Or it could mean flat, dry plains of frozen organic sludge. Or it could mean something no one had a name for yet, because nobody had ever mapped a world like this before.
Ralph Lorenz had to pick a target anyway. A single ellipse on an unseen world, and Huygens would fall wherever that ellipse pointed, whether it was a lake, a rock field, or something in between. Inside the team, the argument got personal.
If we're wrong about the surface, this thing floats for 90 seconds and then it's gone. $3 billion, gone, into a sea we never even confirmed was liquid.
And if we design it only to float, and it lands on solid ground instead, we crush the one instrument that could tell us what's actually down there.
There was no way to test for both. Engineers built Huygens to survive either outcome, sealed like a boat, shaped like a stone. A machine designed to not know, in advance, which world it was about to become. Nobody had ever built a spacecraft this way before. You don't usually design for a coin flip.
4 years, that uncertainty just sat there, unresolved, while the spacecraft crossed the solar system toward Saturn. Then, 3 weeks before Huygens was scheduled to separate and begin its fall, Cassini took one photograph that changed everything Lorenz thought he knew about where they were landing. 3 weeks before separation, Cassini's camera catches a break in the haze over the planned landing zone. Lorenz stares at a mosaic of bright ridges cut by dark, branching channels, patterns that on Earth mean exactly one thing: flowing liquid, carving a path downhill over time. Riverbeds. Not proof of a lake underneath the probe, but proof that liquid moves across this ground, somewhere, sometimes. That single image doesn't answer whether Huygens will float or shatter. It just changes what shattering might look like.
January 14th, 2005. Saturn system, 1.2 billion kilometers from Earth. Huygens separates from Cassini and begins a 3-week fall, alone, radio silent, toward a moon no spacecraft has ever touched.
It hits the atmosphere at 20,000 kilometers per hour. A heat shield glows white, then the parachutes deploy, and for the next 2.5 hours Huygens drifts down through 200 kilometers of orange haze, the thickest, coldest fall of any landing ever attempted.
This is where the methane cycle finally shows itself, mid-fall, in real data. On Titan, methane does everything water does on Earth, just at a temperature cold enough to freeze oxygen. It evaporates from lakes, rises, cools into clouds, and falls back down as rain. The chemistry is stranger than the mechanism. Methane stays liquid at -179 degrees Celsius because Titan's atmospheric pressure is 1.5 times Earth's, high enough to hold it there instead of letting it boil straight into gas. So it rains. Then it pools, evaporates, rises, and rains again, forever, in a loop that has run for hundreds of millions of years without a single drop of water involved.
Back in mission control, on Earth, nobody knows any of this is confirmed yet. The data is still hours away, crawling back across the solar system at the speed of light, which out here still feels unbearably slow.
We won't get real-time video. All we get is telemetry, numbers, and a sequence of images we won't even see until this thing has already lived or died.
90 minutes of battery. That's the whole budget once it lands, if it lands intact at all.
At 6 meters per second, Huygens touches down. It doesn't shatter. It doesn't sink. The surface gives slightly, like wet sand, and the probe settles upright, intact, transmitting. The instrument's red damp ground just beneath a dry crust, the way a beach reads after the tide goes out. Around the lander, smooth, rounded stones, the exact shape water gives rocks on Earth after centuries of being tumbled downstream.
Quick question while we are here. Would you have spotted it? Write your answer in the comments.
Except no water ever touched these. Every pebble here was shaped and carried by liquid methane, over a timescale nobody can precisely date, in a place 1.4 billion kilometers from the sun. These become the first, and still the only, photographs ever taken from the surface of a world in the outer solar system. Every other image we have of Titan's ground is radar, or guesswork, or a horizon glimpsed from orbit. The batteries hold for 90 minutes, exactly as designed, not a second of margin to spare. And in the last few minutes before Huygens goes silent forever, one more reading comes through, something nobody had built the mission to find. 10 years after Huygens went silent, Cassini is still circling Saturn, and its radar keeps staring down at a lake called Lejeune Mer. It is roughly the size of Lake Huron and Lake Michigan combined, filled not with water but with liquid methane and ethane, sitting under an orange sky at -179 degrees. By every rule of liquid we know from Earth, this should look and behave like an ocean anywhere else.
It does not. Radar works by bouncing signal off a surface and reading what comes back. Water on Earth, even on the calmest day, sends back a rough, broken echo, because wind never fully stops and waves never fully die. Lejeune Mer sent back almost nothing. A surface that flat means waves smaller than a few millimeters, or no waves at all, on a lake wider than some seas on Earth. Ralph Lorenz spent years trying to explain that stillness.
If the wind out there is nearly gone, then something about Titan's thick air is smothering it before it ever touches the liquid.
But that only explains why it's calm. It doesn't explain why it barely conducts heat the way a real hydrocarbon lake should.
So we're left guessing at the chemistry of a lake we've never touched.
Then, in 2013, something appeared on the radar images that had not been there before, a bright patch, roughly 160 square kilometers, about the footprint of a small city, sitting in open liquid where there should have been nothing at all. 2 years later, it was gone. A year after that, a similar feature turned up elsewhere on the same lake. The leading explanation is nitrogen. Titan's atmosphere is mostly nitrogen gas, and some of it dissolves into the liquid methane the way carbon dioxide dissolves into a soda. Warm it slightly, or stir it, and that nitrogen can come out of solution as bubbles, or as a slush of frozen solids that rises, floats, and then sinks again as it cools and dissolves back in.
vanishing islands, made of frozen bubbles, rising and sinking on command of a thermostat nobody controls. We'll come back to that same trick of chemistry in a minute, because it turns out methane doesn't just sit still in that lake. It also evaporates differently than water ever does on Earth, and that difference changes what actually reaches the ground when it rains. On Earth, rain falls roughly the same whether it starts 100 meters up or 10 kilometers up. On Titan, models built from Cassini's data suggest something stranger. In the thin, cold air near the ground, falling methane droplets can evaporate back into gas before they ever land, turning a downpour at altitude into nothing at all at the surface.
Rain that never arrives.
A lake too smooth to make sense. Islands that shouldn't float, weather that quits halfway to the ground. And then Cassini's radar caught one more thing sitting on that same lake, a feature so far outside every model that, more than a decade later, nobody has fully explained it.
That unexplained feature on Ligeia Mare turned out to be temporary. Cassini's radar caught a bright patch on the lake's surface in 2013, then watched it fade by 2014. The best explanation researchers have is nitrogen bubbles or a floating slush of frozen organics, rising, then sinking again.
Nobody has watched it happen a second time. So the Phantom Island stays exactly what it was the day it disappeared. A footnote nobody can close. Ralph Lorenz never stopped thinking about that thick, heavy air. Back in the 1990s, while other scientists argued over where Huygens should land, he was already sketching something else entirely. A flying machine built for a world where wings barely have to work. Colleagues thought it was a nice thought experiment. Nothing more.
You keep saying we could fly a drone there. On Mars, we can barely keep a helicopter in the air for 90 seconds.
If you made it this far, hit subscribe and the bell. The next investigation is already in the works.
That's exactly the point. Titan's air is thick, its gravity is weak. We wouldn't be fighting the sky there, we'd be riding it.
30 years after that argument, NASA said yes. The mission is called Dragonfly, a nuclear-powered, drone-sized rotorcraft built to hop across Titan's dunes and crater floors from one landing site to the next, something no other planetary mission has ever attempted. Its price tag, roughly $3.35 billion. That's more than the entire budget of the Perseverance rover mission to Mars, cost overruns included. Why spend that much on a moon 1.5 billion kilometers away? Because nowhere else in the solar system offers this exact combination. An atmosphere thick enough to fly through, organic chemistry raining from the sky, and surface conditions that may resemble Earth billions of years before life ever started here. Lorenz's old sketch is now hardware, scheduled to leave Earth in 2028 and reach Titan in the mid-2030s. The engineer who once argued that flying there should be easier than flying here will get to find out if he was right.
For now, the methane still falls, the rivers still cut their channels, and somewhere under all that orange haze, a lake keeps a secret Cassini only glimpsed once. What Dragonfly finds when it finally lands may decide whether Titan is just a strange moon, or the closest thing we have to watching our own planet's first chemistry happen twice.